Okay, so let's welcome the next speaker, Shiva Theja Maguluri. He's a Fouts Family Early Career Professor and an Assistant Professor in Industrial and Systems Engineering at Georgia Tech. Before Georgia Tech, he has spent 2 years as research staff in the Math Sciences Department at IBM TJ Watson. Before that, he was a graduate student at EC Urbana-Champaign.
Thanks, Karthik. Thanks for the introduction. And thanks to the organizers for inviting me. Today, I'm going to talk about stochastic approximation for finding fixed points. And if you attended Prashant's talk yesterday, you'll see a lot of similarities. So I'll try to make some connections. So this is joint work with my former student Siva and my former postdoc Martin, as well as Karthik and Sanjay. So what I'm interested in, what I'm going to talk about today is solving a fixed point equation. So X for me is a vector in RD, and F bar is an operator. Operator just means it takes a vector, spits out a vector. So I just want to find a X star, a vector X star that satisfies this. And it is well known that if you start with your favorite X0 and then keep repeatedly applying F bar, then it converges to the fixed point if the F bar is a contraction. So this is called the Banach fixed point theorem. So what do I mean by contraction? If you have two vectors X and Y, and you apply the F bar operator to them, then you get two new vectors F bar X and F bar Y, and the distance between these is less than the distance between X and Y. And as long as this is true, Banach fixed point theorem guarantees the existence of fixed point and that you would converge geometrically fast. Banach fixed point theorem is very general. It works for arbitrary norm. It also works in infinite dimensional spaces, but we'll only focus on RT. So what I'm interested in is the case when this F bar is not known. However, I have an access to a noisy oracle. I give it X. The oracle's job is to give me F bar of X, but it adds some noise. And this noise can be IID, martingale difference, Markovian, and so on. We'll talk more about the assumptions as we go along. Then the question is, what should I do? Should I just pretend the noise is not there and just keep using this iteration? And stochastic approximation is an algorithm that was introduced by Robinson Monroe in 1950s. And what they suggested is that instead of simply using this, do a convex combination between xk and this noisy F bar. And alpha is my convex combination parameter. And I'm making it a function of k. The idea is that, let's say that I start my algorithm from X star, the fixed point. If the noise was not there, I would know it immediately because I apply F bar and I don't move, so I know I'm at the fixed point. But in presence of the noise, even if I start at X star, I'm kind of being pushed around. So the idea is after a long time, if I'm close to X star, then I want to give less weight to this noise. That's the reason I want to make this alpha decreasing over time. And this same update can be equivalently written like this. And this is called the stochastic approximation. So the first question that one can ask is, does this work? And by the way, before that, I also want to point out that I'm interested in arbitrary norms. So I said we have a contraction. Whenever we talk about contraction, we should talk about a particular norm. And the simplest norm, of course, is the L2 norm. But I'm going to be interested especially in L infinity norm. But all the results I'm presenting today are true for arbitrary norm in RT. Okay, so the first question is, does this work? And the answer is yes. And there's a long line of literature from the 50s to about 1990s, where using ODE method, using martingale techniques, one has it was proved that this algorithm works in the sense that almost surely, asymptotically, you converge to the X star under appropriate assumptions on the noise, step sizes, and so on. What I'm going to be interested in today is how well does this work? In other words, what is the rate of convergence? What are the finite sample bounds? So this is the outline of my talk. I'll continue talking about stochastic approximation. Introduce stochastic approximation with some examples. And then I want to present rate of convergence. And my iterates xk are random. They're random because of the noise. And I'm interested in the rate of convergence of xk to x star. There are many ways of talking about rate of convergence. One is in terms of the mean square error. That will be my next focus. And after that, I'm going to talk about a different way of characterizing rate of convergence in terms of tail bounds on xk minus x star. So I want to say that with high probability, this error is less than blah. And depending on how much time I have, I'll talk about the proof, high level idea of the proof in both the cases. So feel free to stop me at any point of time if you have any questions. Okay. Cool. So why am I interested in this problem? So Prashant nicely motivated yesterday that in many reinforcement learning problems, you're interested in solving the underlying Bellman equation. And the Bellman equation is a fixed point equation. In his talk, Prashant primarily focused on TD learning, where the fixed point equation has a linear structure. But if you look at Q learning and so on, then we don't have linearity. So I cannot exploit linearity, but the contraction structure is something that remains, but the underlying norm is different in different settings. I also want to point out another simpler example, which I'll come back to in my talk. So suppose I want to simply solve an equation Ax equal to B. There are many, many ways of doing this, Gauss elimination, I can invert the matrix and so on. And but I'll only focus on the cases where A is Hurwitz. Hurwitz means that the eigenvalues of A have negative real parts. And it can be shown that whenever A is Hurwitz, then I want to write this as a fixed point equation. So what I do is I send this B onto the other side, multiply the whole thing by some constant eta, and then add x on both sides. Then what I end up on the left-hand side is this guy. So it can be shown that whenever A is Hurwitz, with appropriate choice of eta, I can, this is a contraction. So it fits into my framework. That's all I'm trying to say. And then if I substitute this particular choice of f bar here and simplify it, essentially my linear stochastic approximation looks like this. And if A and B are known, like we were talking, we could invert A, we could do Gauss elimination and so on. But now I'm interested in the case where either A or B or both of them could be noisy. Then linear stochastic approximation will lead to a solution of this. And sorry? That's a very good question. That's what Prashant talked about yesterday. I'm going to bypass that question. So the choice of eta is going to depend on the largest eigenvalue of A. I mean, the smallest in terms of magnitude. And eta, I'm assuming that I know what that guy is and I can pick eta appropriately. Otherwise, usually if you're doing diminishing step size, then after some point, all these assumptions will kick in anyway. So it's okay in practice. Cool. So even though there are many, many ways of solving linear system of equations, especially in presence of noise and in high dimensional cases when X is in RD where D is large, linear stochastic approximation is one of the most preferred methods. Another example I want to point out is optimization. So suppose I have a function f and let's say it's smooth and strongly convex and I want to minimize it. Minimizing a function is same as finding an x such that the gradient is equal to 0. Yes. No, not necessarily. I also have this I plus thing. Yeah. So it doesn't quite work. It works only for Hurwitz. Yeah. Okay, any other questions? Okay, so in optimization, again, I want to solve gradient of f of x equal to 0. And to make it look like fixed point, I multiply by eta and then add x. And again, one can show that this is a contraction whenever f is a smooth strongly convex function for appropriate choice of eta. And then if we substitute this value of this particular value of f bar in this equation, what I get is the famous stochastic gradient descent algorithm. Yeah.
But if I get plus eta, it becomes a gradient.
Yes.
Kind of not very intuitive as to why.
Correct. In this case, in optimization case, yeah, that's right. But I need contraction. I think in the smooth strongly convex case, only if I put minus eta, I get contraction. Otherwise, I don't. That's correct. Right. By the way, this is kind of silly way of getting a fixed point by adding by multiplying eta and adding x. There are many other cleverer ways of getting fixed point equations for optimization problems, and there's a whole area doing that, and I'll not get into it. Okay, so this is my motivation. So let me just jump right in and present the results. I'll start with the mean square bounds. But before I present the results, I want to make my setting and assumptions more formal. So I said I'm trying to solve f bar of x equal to x. The reason I put bar is because I was hiding something underneath, and now I want to show you what I was hiding. So my f is not a function of x alone; it's a function of another variable y, and this y is also going to be noisy. So my stochastic approximation, instead of having f bar of x here, I have this f of x comma y. So my w was anyway noise, Now I'm introducing a second source of noise. Why? I could have called this whole thing a single quantity, because I can make different assumptions on Y and W, and that turns out to be important in some of the applications, especially in reinforcement learning. So my motivation for doing this comes from reinforcement learning. So I'm going to assume that Y is a Markov chain. And for simplicity, I assume it is finite state. It has to be ergodic. Ergodic means that it irreducible and aperiodic. But finite state is for simplicity. If I assume Y is finite, I get that it is geometrically mixing. If I don't assume that, I have some mixing. I need fast enough mixing. And the stationary distribution of this Y is mu, and F bar is an expectation of this F of X comma Y, where the expectation is taken with respect to the stationary distribution. Right. And W can be either IID or martingale difference. And not able to see the slides. Okay, cool. So W, I'm going to assume is IID or martingale difference. And normally in optimization literature, one assumes that this W has a bound that is bounded, like variance of W is bounded. But here we allow that W can grow with X. So, and this also turns out to be important in reinforcement learning. And I also want to introduce some terminology. I want to call Y multiplicative noise and W additive noise. This is a terminology that we introduced. And the reason for this is, let's go back to the linear stochastic approximation. I said, I want to solve AX equal to B. Then there are two settings. A is known, B alone is noisy, or both A and B are noisy. And suppose A is fixed and B alone is noisy, then it's like the noise in B can be modeled by W, and the noise in A can be modeled by Y. And the key thing about the noise in A is that my iterate is getting multiplied by this noise. And that's what makes it challenging. Okay. So, yes.
The law of WK can depend on YK. I presume that is a state or something.
Right. Yes.
So it's not just, so when you say martingale difference, it's with respect to the natural filtration.
Exactly. Yes. So martingale difference means that the conditional expectation is 0, but if it's a Markov chain, conditional expectation is not 0. That's the reason I have to model it separately. Yeah. Here I'm assuming it holds almost surely, but in some settings you can get rid of this and then just assume that in second moment you have a bound like this. In fact, actually for reinforcement learning applications, I don't even need W. W can be 0. I only have Y. We put W just for generality. Any other questions? Okay, good. And I also have a couple more assumptions on F, essentially Lipschitz properties and certain boundedness assumptions. I'm not presenting them here for simplicity. But the key thing is that this expected F bar, is a contraction, and I'm allowing it to be an arbitrary norm, need not be L2 norm. Okay. Under these assumptions, we have the following results. So firstly, choice of step size. Step sizes in stochastic approximation need to be decreasing, and they need to be non-summable but square summable. And we have results for various choice of step sizes, but since we have limited time, I'll just focus on step sizes of this form. And this alpha is important. I'm assuming that this alpha is large enough. And this large enoughness depends on the problem parameters. Prashant yesterday talked about what if you don't have that, you have to do tail averaging and so on. I'm not going to get into any of that. I just assume that I can pick this alpha large enough. Then the main result I have, sorry, ignore this infinity for the time being. The main result I have is that the mean square error is going to 0. And it's going to 0 as 1 over k with this log k in the numerator. I don't think this log k is needed, but it's an artifact of our proof. If y was IID, we can get 1 over k rate. But when y is Markov, we can only show log k, but getting rid of that log k is ongoing work. Whatever norm is there, it's the same norm actually. Correct. Yeah. And once you come here, you can put whatever norm you want because all norms are equivalent in RD, so this concept will be different. That's all. Yeah. But you can't do that at the contraction level. There, if you do norm equivalence, your gamma will become greater than 1. Okay, good. So I'm hiding a lot of things in the C. In fact, what happens is, if you recall Prashant's bounce yesterday, he has two terms. The first one where the initial error is decaying, and the second one which is the dominant. We have something very, very similar, but again, for simplicity, I'm focusing on just the dominant term. There is the initial error dependence hidden here. And the C is hiding a lot of things. And some of the things that C is hiding depend on the underlying norm. So now let's suppose that the underlying norm is infinity norm. In this case, the C has a log D hidden in it. So if it was a 2 norm, there would not be any dimensional dependence at all. And that's the reason why SGD is so popular, because there's no dimensional dependence. But if it's an infinity norm, a log D shows up. And we believe this is not an artifact of our proof. It's inevitable because infinity norm is kind of like max. So if you have max of D Gaussians, then their square is like log D. So this log D is inevitable. No, actually, this is at this point, I'm only in the stochastic approximation setting. If you translate this to reinforcement learning, there'll be 1 minus gamma power 5. There's another 1 minus gamma square that comes from somewhere. And that is not optimal. So the state of the art is 1 minus gamma power 4. And I think this 5 to 4 is just a consequence. I think something is probably not tight in our analysis. But the 4 can further be improved to 3. But for that, you have to do something more in the algorithm, like variance reduction. I mean, in the first result, I didn't even tell you what C was. So if the underlying norm is 2 norm, then there is no dimensionality dependence. Yes. But if it is infinity norm, then we get log D. Right. Correct. Yes. The log K we can't get rid of. That's an artifact of our proof. Again, if you have IID sampling, we don't have log K. But if you have Markov sampling, we have log K. Even in tabular TD, we have log K. Yes. But again, we have ongoing work where that can be gotten rid of, but it is still in very preliminary stages. There is no, we do have Markov noise. Actually, we have 2 papers. In the first paper, there was no Markov noise. In the second paper, we do. More questions? Okay, cool. So using this, one can talk about sample complexity. There are many notions of sample complexity. For the time being, let's say that I want the mean square error to be less than epsilon. And then I ask you how long should I run my stochastic approximation. Then you can essentially invert this formula, and then you'll get something like O of 1 over epsilon square. The tilde just means I'm being sloppy with logs. Good. I mean, this is just mean square. So I mean, I can just calculate this and stop at that time. Done. So I'm again bypassing the stopping time issues here. Sorry. Not mean square. It's expectation of the error without the square. Good catch. Thanks. Okay, good. So the main contribution in this part of the talk is about handling the general norm. So in the case of L2 norm, I said SGD is a special case with L2 norm contraction. So the same proof as SGD pretty much works for L2 norm contraction as well. But if it is L infinity norm, and that's a Lyapunov argument. And in the case of L infinity norm contraction, this was an open problem. In fact, there's this nice book, Neurodynamic Programming by Tsitsiklis and Bertsikas from the 90s, where they essentially say that the Lyapunov function is not known for L infinity norm. So we can't directly use SGD proof. So our contribution is essentially to construct a Lyapunov function for arbitrary norm, in particular for L infinity norm. And then once we know the Lyapunov function and its properties, we can essentially replicate the SGD proof to get all these results. And depending on time, I might show you the Lyapunov function at the end of this talk. Yeah. Exactly, correct. No, we don't use that argument. So again, the issue is the same thing. Like if it is L2 norm, Lyapunov function is known. If it is LP norm, then again, Lyapunov function is known. For L infinity, there was no known Lyapunov function. So what Borkar does is he lets P go to infinity. Because he's using the ODE method, he can use continuity arguments. We don't use the ODE method. More questions? Okay. So if there are no more questions, I think I'll skip the related work because I'm running out of time. Essentially, what I want to say is special cases of L2 norm contraction or the linear case was studied in literature. L infinity was studied in the literature, but only in the context of Q-learning, which has other properties. So these other properties were exploited. So in this generality, no result was known in the literature, and our result recovers pretty much all the other results available in the literature. And we do it with new Lyapunov function. So this work is from a couple of years ago. In the next part of my talk, I want to talk about new work on tail bounds. Yeah, we assume fixed behavior policy. Yeah. We don't do two-time scale analysis. I mean, we do two-time scale analysis in other contexts, and here we don't. Okay, good. So far, quick recap, we have the stochastic approximation to solve fixed point equations. And then I said that we have this mean square bound of the form 1/k. And in this part of the talk, I'm interested in getting tail bounds. So I don't like this expectation. I want to say that the error or error square is less than blah with high probability. And the simplest way of doing it is simply use Markov inequality. So if I want to show that this probability of this error square is greater than or equal to whatever this guy is the same guy multiplied by z, then using Markov inequality, we'll get a bound of 1/z. But I'm not happy with this 1/z tail. I want stronger tail bounds. Can I get exponential tail bounds? That's the question. Why? Because exponential decay is much faster than 1/z. And I'm going to state the results more formally in the next few slides, but I want to tell you the punchline. The punchline is yes and no. So if you have only additive noise, no multiplicative noise, then you can get this exponentially decaying bounds. But in the multiplicative noise setting, it's not possible to get these tails. You'll get heavier tails. So this decays as e power minus z, but I like to call this Gaussian tail because I have a square here. If I remove this square, then this becomes square root of z and this becomes square root of z whole square. So this is essentially Gaussian tail. And in the multiplicative noise setting, depending on how bad your noise can be, you can either get Gaussian tail, exponential tail, or heavier than that, Weibulian tail. But nevertheless, these are all lighter than any polynomial tails. So we're going to see that.
Again, usually in regression,
yes,
you have a bias variance decomposition. The multiplicative part of that usually gets into the bias part, and the variance part has a very light tail. Is that you seen here as in it can be written as a light tail plus a heavy tail. But the heavy tail thing has an exponentially small.
I see. So we didn't do the separation, but I think part of it is visible in the fact that if I don't have multiplicative noise, we get this very light tail. But in this case, we did not separate it. Actually, we did only multiplicative noise. I mean, yeah, we didn't separate it. So I don't know how to answer. Okay, good. So what I'm going to do is, so the mean square results are relatively easier to get than tail bounds. I mean, not surprisingly. So the assumptions in the tail bounds are going to be slightly different. So this is the same slide as before on the assumptions for the mean square bound. And I'm going to change this. First, I'll state the additive noise. And in the additive noise case, I don't have multiplicative noise y, so I'll just drop it. Since I dropped it, I don't care about assumptions on it. And here I need to have some assumption on this W because I want exponential tails. The noise better have good tails. So I'm going to assume that it is sub-Gaussian. If it is not sub-Gaussian, I shouldn't expect that the error will be sub-Gaussian. And that's pretty much it. Because actually my result is going to be sub-Gaussian. So if this is sub-Gaussian, that will be sub-Gaussian. Yes. And again, recall additive noise means that I know A, there's no noise in A, B alone is noisy, and the noise of B is sub-Gaussian. So in this case, again, the question I had earlier was this: can I have exponentially decaying tail error on the mean square error? And the same thing can be written like this. So what am I doing? I'm just calling this delta. If this is delta, z is log 1 over delta. So I remove z and put log 1 over delta. And I just reverse the inequality. No, sorry, it's the same thing. So these two are equivalent. And usually in literature, one uses bounds of this form. So I'm going to state the theorem in this form. And the theorem essentially says exactly the same thing. It says that with probability 1 minus delta, and I'm again using this alpha over k kind of step size, and this alpha should be large enough. So with probability 1 minus delta, so my squared error is less than essentially something that looks like this, some constant over k times 1 plus log 1 over delta. So this essentially means that I have sub-Gaussian tails. So I can again talk about sample complexity, but now the sample complexity is of a different flavor. Earlier, I wanted expected mean square error or the mean error to be less than epsilon. Now, the definition of sample complexity is that the error, absolute value, the norm of the error should be less than epsilon with probably 1 minus delta. And the question is, how many samples do I need for that? And using this bound, if you invert it, you can show that the sample complexity is of the form 1 over epsilon square log 1 over delta. Sorry, this should be O tilde. Yeah. No, this is O. There's no O tilde. Sorry. Which one? No. I mean, this one is, when delta is small, this dominates, right? So this is almost irrelevant. I guess if you put delta equal to 1, then, yeah, I don't know. If delta equal to 1, then this is loose, I guess. This one matters. But when delta is small, this one is irrelevant. Correct. There you don't get 1. That's right. I don't know how to answer that question. We don't use the mean square bounds. We get 1 as a consequence of our analysis. Yeah, right. But we are not doing the centering. So that's the usual approach in high dimensional probability. If you want to understand some quantity, you look at its expectation, and then you also look at the deviations from the expectation, and then analyze these two separately, the different tools used for each of these problems. We are not doing any of that. We actually go to the fundamentals, we work from scratch, and we directly bound this guy. Any other questions? Okay, good. So yeah, I already mentioned that this should be thought of as sub-Gaussian tails because of the square. If I remove the square, that square comes up here, and this is sub-Gaussian. Next, I want to talk about multiplicative noise. But before I present the result, I want to explain to you why it is challenging. And to see that, let's think of solving a linear equation with linear stochastic approximation. And let's say b equal to 0. And there is no noise. I mean, every noisy sample is of b is 0. So there's no b, which means the answer to this equation is x equal to 0. There's nothing to do. But I want to run the stochastic approximation just to get intuition. So if b is gone, then it looks like this. And if alpha is appropriately chosen, this guy is going to be contractive. So x is a vector. I'm hitting it with a matrix at every time. I mean, I'm hitting it with random matrices. These A's are random. And the key thing is, in expectation, they're random. But in expectation, they're contractive. The expectation of A is has negative eigenvalues. And so under appropriate choice of alpha, the expectation of this is going to be contractive. But actually, this matrix could be expansive. So I have this vector. I'm hitting it with random matrices. And these random matrices could be expansive or contractive. And but in expectation, they're contractive. So that is the challenge. So if I assume that every random instance is contractive, then I can expect that good things will happen. And in fact, there's some literature that does that, but we don't assume that. So I could be expansive, but in expectation, I'm contractive. So that's the key challenge. How do we deal with this? I'm again going to very quickly, I'm going to skip the literature. All I want to say was that the mean square bounds are known. And there is one particular recent paper where they work with the setting where every instance is contractive, but we don't do that. And of course, we don't do it only for linear. We do it in the full generality of nonlinear, contractive, arbitrary norm, all of that. This is just a special case. Okay, yeah. Here I'm going to assume it is IID. I'm going to show it in the next slide. So Markovian setting here is ongoing work. Sandeep's former student Shubhada is my postdoc. She's working on it. She told me she finished it. I have to go back and check. Okay, then. Yeah, but then this x is multiplying. That's the source of all difficulties. You can do that, but x is multiplying. No, not here. In the mean square result, I did that. In the additive result here, it's sub-Gaussian with a fixed parameter. Maybe that was unclear. Yeah, that's the reason I distinguished between these two in the tail setting and not in the mean square setting. How much time do I have? Okay, so again, I want to state the assumptions. These are the assumptions from the mean square setup. Now I'm going to assume I only have multiplicative noise. So I'll throw away the additive noise and I'll throw away the corresponding assumption. Earlier, I assumed this Y was a ergodic Markov chain, finite state space, all of that. Now, this is what I want in order to apply this result for reinforcement learning. But unfortunately, we still don't know how to analyze Markov chain, like I just said. Instead, I'm going to assume it is IID. It has some stationary distribution mu. That is the one that shows up here. And it has bounded support. Y has bounded support. More precisely, the assumption is something like this, but you can think of it as the A as having bounded support. Okay, and the contraction thing has not changed. Now, under this assumption, why do we make this bounded support assumption? Because if you don't have bounded support, if you assume this A is sub-Gaussian, for example, then if you run this iterate, in 3 time steps, MGF does not exist. And after that, the tail becomes heavier with time, and in that setting, you can't do anything basically. So that's the reason we need some assumption and we are working with the boundedness. Okay, good. So now here is the result. So again, appropriate choice of alpha in the step size. Then the error, the squared error with probability 1 minus delta is bounded like this. So if you remember the additive noise setting, we just had C over K times 1 plus log 1 over delta. All that has changed is there's a M here. This M is a problem dependent parameter. In fact, what is it? I told you that my operator is random. Sometimes it's contractive, sometimes it's expansive, and in expectation it's contractive. But because of my boundedness assumption on the noise, when it is expansive, it can't be infinitely expansive. It is expansive up to some bound, and let's call that B, and that B is greater than 1. This M characterizes, this M is essentially that B plus gamma minus 1. So this M characterizes how expansive I allow it to be. If this operator can be very expansive, then the tail becomes worse and worse. That's the idea. It doesn't depend on the distribution explicitly, it only depends on the maximum of the support. So if the support of A, I mean I plus alpha A, the expansiveness of it is up to, I don't know, 5, then this M is close to 5. Correct. I mean, I don't know, loose or not, because many bounds, like there are many things like, so in the mean square setting, for example, our bounds are tight in some sense, in the sense that you can find a counterexample that matches it, but these are not instance dependent. So we have the same thing. In fact, I was going to say that. We have a counterexample that matches this, this M. But I guess maybe you can find other examples where there is some gap. Okay, and this M in the exponent here, if you write it the other way in terms of the tail, you would get Z power 2 over M. Which means if M equal to 1, this is like sub-Gaussian tail. If M is 2, it is exponential tail. And if M is greater than 2, then this is called Weibulian tail. So, but this is always some kind of exponential form, but this is lighter than any polynomial tail. So this is always lighter than what you get by using Markov inequality on the mean square bound. Okay. Good. Any questions on this so far? Everything is known. Everything is very, very explicit. Yes. Yeah.
So there is this recent work about heavy-tailed, they use an estimate, heavy-tailed mean estimate by using clipping. They show that you can still achieve sub-Gaussian rates by even when you have some.
Right. We didn't do any of that. I think that's a natural next step. So we basically took Robbins-Monroe. We did not touch the algorithm, and then this is what you get. Then I guess the next question is, can you make the tails lighter?
But you control the bias.
The iterates can potentially go to infinity. That's a very good question. So yeah. Okay. 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 Oh, wait. In RL, we assume that the rewards are bounded by 1. But there is randomness within. Okay. Sorry. Right. Okay. So there's a gap between this and RL. So firstly, here I want to point out that we don't assume the iterates are bounded. In fact, in the multiplicative noise setting, if you assume iterates are bounded by possibly projecting onto a finite set like you do in optimization, or for whatever other reason, if your iterates happen to be bounded, then you'll again get Gaussian tails. So in the bounded iterate case, the results are similar to the additive noise case. The key challenge here is these iterates can potentially be unbounded. And in the worst case, they will be unbounded, and then we are trying to bound the tails. So that's the challenge. So this is in the stochastic approximation setting. Now, when you translate this to RL, the two cases, tabular and function approximation. In tabular setting, you can show that the iterates are bounded if you assume rewards are bounded and finite state. Therefore, you can get sub-Gaussian tails. There's no problem. You don't need to look at this setting. But in the function approximation setting, the iterates are potentially unbounded, and there these Weberian tails can show. Right. Correct. That's because in RL, the iterates are bounded in the tabular setting. That's why. So in the tabular setting, the variance, what you're thinking is the W depends on X, but X itself is bounded. So put that bound in it, so it's a constant upper bound. Yes. In RL tabular setting. Yes, correct. That is additive case. Here, that's not the case. So I want to make this distinction. No, if you do TD LFA, this is the one that you have to use. You can't use the other one. Five more minutes? Okay. In tabular RL, it can be shown that if rewards are bounded and you have finite states, then the iterates are bounded. That is classical, that's known. In function approximation, because you're multiplying by these feature vectors, you don't have boundedness. Okay. Any other questions? Okay, good. So, it turns out that this bound that I showed is only after some time. And up to that time, we have a bound that goes up, which is ridiculous because I want the error to go down. And why does this go up? So pictorially, our bound looks like this. After some time, I have this 1 over k with this Weberian tail. Up to that, it goes up. And why does this happen? So we actually did a simulation, and you see that it indeed goes up in the beginning and it comes down. And that's because, like I was saying, you're hitting it with this expansive operator once in a while. And we're looking at the tail, which means it is in some sense worst case. So it is possible that in the beginning, you're unlucky and you just see these expansive operators. Then your error will go up. But the reason that eventually things will be okay is because averaging kicks in. And for average to kick in, for Chernow bound or Hovding bound or some concentration to kick in, you need some log 1 over delta amount of time. And that's the reason up to this time, we only have a bound that goes up. And then after that, it goes down. So since I have less than 5 minutes, so I want to talk about proof sketch. So I had 2 parts in the proof sketch, the mean square part, where the key contribution was constructing a Lyapunov function, where we use something called the Moro envelope and informal convolution. But I'll skip that part. I'm happy to chat about it offline with anybody that is interested. But let's focus on the tail bounds. So for the tail bounds, we have 3 steps in the proof. The first step, if you have additive noise setting to get the first theorem, you can just stop at step 1. You don't need step 2 or step 3. And if you can prove that the iterates are bounded due to other properties of your algorithm or due to projection, then again, you can stop at step 1. But if you don't have either of these 2, and in that case, you get Gaussian tails. If you don't have either of these 2, then you need 3 steps, and then you would end up with Weberian tails. Now, what is the, okay, so let me skip this and let me just jump right into first step. So let's focus on 2-norm contraction for the time being so that we can make everything concrete. Then this M is simply x minus x star norm square. That's a Lyapunov function that works in SGD proof for mean square error. And so I said that if I had the mean square error, I could use Markov inequality, I'll get 1 over k tail. But I want exponential tail. So the natural thing to do is to get a bound on the MGF of the error. If I can bound the MGF of the error, then I can again use Markov inequality, I'll get exponentially decaying bound. That's the idea. But this by itself does not work, unfortunately. You have to massage it a little bit. What you have to do is the following. So remember, this is what I was trying to do all along. There's a 1 over k here. I can bring this k here, nothing changes. So I wrote the same equation like this. Now I can think of this as bounding this guy with a k inside it. So if I want to use the same trick, I would put a k in the exponent. And this turns out to be the right Lyapunov function. So this is a time varying Lyapunov function. It depends not only on my x, but also k. And in the case when you know the iterates are bounded, you can also put that bound of the iterates in the exponent in the denominator. And we can show that this works as a Lyapunov function, which means we can get a recursion on this. And by solving the recursion, we can get a bound on this MGF. And inverting that, we get the exponential tail bound. But then step 2, I'll not get into the details, but step 2 is to make this bound anytime by using martingale arguments. So let me skip that. But I want to go to step 3. So again, like I said, if you do step 1 and step 2, what you have is, let's say you're looking at the case where the iterates are bounded. In this case, you start by assuming iterates are bounded. Then you show that your iterates are less than 1 over k with high probability. By high probability, I mean the Gaussian tail. Now, in the multiplicative noise setting, the iterates need not be bounded, but we know that they need not be bounded by a constant, but they can be bounded by this increasing function. So I can pretend this increasing function is a constant, go through my steps, surprisingly everything works, and what I end up is 1 over k times this bound. So if m was 100, I start with my iterates being bounded by k power 100, then I ended up with k power 99 with high probability. Now I can repeat this. I can repeat this 101 times. So essentially inductively repeat this. We call this bootstrapping. Then at the end of it, you get 1 over k with high probability. But every time you do this argument, you're losing a little bit of the tail. And that's why the tail becomes heavier and heavier. And that's why the same parameter m shows up in the tail. So pictorially, initially we show a bound like this. Then each step, it keeps going down, down, down until we get 1 over k. So that's it. I'll stop here. I don't have to go to the conclusion slide if we are running out of time. Thanks. Any other questions, Gugan? No, I'm not aware of that work. So the bootstrapping idea itself is like not necessarily in concentration. It's, I mean, many people have used it in the literature. We didn't invent it. Within the context of concentration also, some people have used something that looks like bootstrapping. We have looked at a lot of work extensively, but there's no result that is of this flavor. Like either you have some boundedness, or you do it for constant step size and the constant should depend on epsilon and delta, things like that. I can tell you more about it, but I don't think we looked at this particular paper. Firstly, we don't have Markov noise, so you can compare. But if you look at TD with, let's say IID is a special case of Markov, then there are no results in the literature that are of this flavor. Maybe we can talk offline about what the differences are. Yeah. Yes. Yes. So it's not that the Lyapunov function is time dependent, but the idea is that there's that m is the mean square error, not mean square, it's the square error. We know that the mean square is like decaying as 1 over k. K is the right rate, so I'm putting it in the exponent. So intuitively, this k times m should be like order constant. So that's the intuition for it. But of course, when you use that Lyapunov argument, I mean, if you think of it as an ODE and you differentiate, there's a T, that K is T, right? You have to differentiate with respect to it. So there'll be additional terms and you have to deal with them. But turns out this is the right thing to do.